in the videos on massive stars and on black holes, we learned that if the remnant of a star, of a massive star, is massive enough, the gravitational contraction, the gravitational force, will be stronger than even the electron degeneracy pressure, even stronger than the neutron degeneracy pressure, even stronger than the quark degeneracy pressure, and everything would collapse into a point. And we called these points black holes. Black holes. And we learned there's an event horizon around these black holes. And if anything gets closer or goes within the boundary of that event horizon, there's no way they can ever escape from the black hole. All it can do is get closer and closer to the black hole. And that includes light. And that's why it's called a black hole. So even though all of the mass is at the central point, this entire area, or the entire surface of the event horizon, I'll do it in purple because it's supposed to be black. This entire thing will appear black. It will emit no light. Now, these type of black holes that we described, we call those stellar black holes. Stellar black holes, and that's because they're formed from collapsing massive stars. And the largest stellar black holes that we've observed are on the order of 33 solar masses, give or take. 33 solar masses. So very massive to begin with. Let's just be clear. And this is what the remnant of the star has to be. So a lot more of the original star's mass might have been pushed off in supernovae. Plural of supernova. Now, there's another class of black holes here. And these are somewhat mysterious. And they're called supermassive black holes. Supermassive black holes. And to some degree, the word super isn't big enough. Supermassive black holes, because they're not just a little bit more massive than stellar black holes. They're a lot more massive. They're on the order of hundreds of thousands to billions of solar masses. 100,000 to billions times the mass of our sun. Solar masses. And what's interesting about these, other than the fact that they are super huge, is that there doesn't seem to be black holes in between, or at least we haven't observed black holes in between. The largest stellar black hole is 33 solar masses, and then there are these supermassive black holes that we think exist, and we think they mainly exist in the centers of galaxies. And we think most, if not all, centers of galaxies actually have one of these supermassive black holes. But it's kind of an interesting question. If all black holes were formed from collapsing stars, wouldn't we see things in between? So one theory of how these really massive black holes form is that you have a regular stellar black hole in an area that has a lot of matter that it can accrete around it. So let's imagine you have a regular, so I'll draw this is the event horizon around it. The actual black hole is going to be in the center of that, or the mass of the black hole will be in the center of it. And then over time, you have just more and more mass just falling into this black hole. Just more and more stuff just keeps falling into this black hole, and then it just keeps growing. And then it just keeps growing. And so this could be a plausible reason, or at least the mass in the center keeps growing, and so the event horizon will also keep growing in radius. Now, this is a plausible explanation based on our current understanding. But the reason why this one doesn't gel that well is if this was the explanation for supermassive black holes, you expect to see more black holes in between. Maybe black holes with 100 solar masses, or 1,000 solar masses, or 10,000 solar masses. But we're not seeing those right now. We just see the stellar black holes, and we see the supermassive black holes. So another possible explanation, this is where my inclinations lean towards this one, because it kind of explains the gap, is that these supermassive black holes actually formed shortly after the Big Bang. That these are primordial black holes. These started near the beginning of our universe. Primordial black holes. Now remember, what do you need to have a black hole? You need to have an amazingly dense amount of matter, or a dense amount of mass. If you have a lot of mass in a very small volume, then their gravitational pull will pull them closer and closer together, and they'll be able to overcome all of the electron degeneracy pressures, and the neutron degeneracy pressures, and the quark degeneracy pressures to really to really collapse into what we think is a single point. I want to be clear here too. We don't know it's a single point. We've never gone into the center of a black hole. Just the mathematics of the black holes, or at least as we understand it right now, have everything colliding into a single point where the math starts to break down. So we're really not sure what happens at that very small center point. But needless to say, it will be an unbelievably, maybe infinite, maybe almost infinitely dense point in space, or dense amount of matter. And the reason why I kind of favor this primordial black hole, and why this would make sense, is right after the formation of the universe, all of the matter was in the universe was in a much denser space because the universe was smaller. So let's say that this is right after the Big Bang, some period of time after the Big Bang. Now, what we've talked about before when we talked about cosmic background radiation is at that point, the universe was relatively uniform. It was super, super dense, but it was relatively uniform. So a universe like this, there's no reason why anything would collapse into black holes. Because if you look at a point here, sure, there's a ton of mass very close to it, but it's very close to it in every direction. So it would be pulled, the gravitational force would be the same in every direction if it was completely uniform. But if you go shortly after the Big Bang, maybe because of slight quantum fluctuation effects, it becomes slightly non-uniform. So let's say it becomes slightly non-uniform. But it still is unbelievably dense. So let's say it looks something like this, where you have areas that are denser, but it's slightly non-uniform, but extremely dense. Extremely dense. So here all of a sudden you have the type of densities necessary for a black hole, and where you have higher densities, where it's less uniform, here all of a sudden you will have inward force. The gravitational pull from things outside of this area are going to be less than the gravitational pull towards those areas. And the more things the more things get pulled towards it, the less uniform it's going to get. So you can imagine in that primordial universe, that very shortly after the Big Bang, when things were very dense and closely packed together, we may have had the conditions where these supermassive black holes could have formed, where we had so much mass in such a small volume, and it was just not uniform enough so that you can kind of have this snowballing effect, so that more and more mass would collect into these supermassive black holes that are hundreds of thousands to billions of times the mass of the sun. And this is maybe the even more interesting part, those black holes would become the centers of future galaxies. So you have these black holes forming, these supermassive black holes forming, and then as not everything would go into a black hole. Only if it didn't have a lot of angular velocity, then it might go into the black hole. But if it's going past it fast enough, it'll just start going in orbit around the black hole. And so you can imagine that this is how the early galaxies, or even our galaxy, formed. And so you might be wondering, well, what about the galaxy at the center of the Milky Way? Or sorry, what about the black hole at the center of the Milky Way? And we think there is one. We think there is one because we've observed stars orbiting very quickly around something at the center of the universe. Sorry, at the center of our Milky Way. I want to be very clear, not at the center of the universe. And the only plausible explanation for it orbiting so quickly around something is that it has to have a density of either a black hole or something that will eventually turn into a black hole. And when you do the math for the middle of our galaxy, the center of the Milky Way, our supermassive black hole is on the order of 4 million times the mass of the sun. So hopefully that gives you a little bit of food for thought. There aren't just only stellar collapsed black holes, or maybe there are, and somehow they grow into supermassive black holes, and that everything in between we just can't observe. Or that there really are a different class of black holes. They're actually formed different ways. Maybe they formed near the beginning of the actual universe, when things the density of things was a little ununiform. Things condensed into each other. And we're going to talk about in the next video is how these supermassive black holes can help generate unbelievable sources of radiation, even though the black holes themselves aren't emitting them. And those are going to be quasars.